methods. So I want us to look into applications where we deal with Newton's Taylor method. Really. So this is supposed to be Y Taylor method. Or we used to call it Newton's Raphson method. Raphson method. So how or where do we apply it? So in functions, uh, for an example, if let's say we want to determine roots, so it helps us to get the roots, So for an example, where maybe with factorization, or maybe if you're trying to utilize the quadratic formulae to get the roots, you want to get the roots of f of x. So as I was saying, so to get the roots for some functions where you can't even use the general methods that you're used to determine the roots of a function. Remember, when we talk about the roots, this is the x values where y is equals to 0. So we know that this is where, let's say maybe f of x is equals to 0. So for a function f of x where it is equals to 0. So we have formulae that you can use. Let's say general one will be written in this way. So it will be xn plus 1 equals to xn. So this is the initial value that you are given as a root. So this is a approximation better than xn. So which means this initial one, when approximate, we will have to get at least the better or approximated root. Then the formula will be minus. Therefore, we'll have so it's f prime of x, f prime of x, all divided by, okay, it's f of x all divided by f prime of x. So we'll be substituting xn there, the initial value. So we'll be substituting the initial value. So I wanted to draw the formulae where it's written. So we have it here. So xn plus 1, xn minus xn all divided by f of prime of x fn. So as I was mentioning, so the normal one that we used to, the Newton's, we used to call it the Raphson method. So it's R equals to A plus E. So here, for an example, it means that the error in approximation, this is E, this is error in approximation, it will be given by f of A, therefore all divided by f prime of A. So when you substitute A. So this is the error in the approximation, and therefore R, it is the better approximation than A. So this is the better approximation than A. So in certain functions, let's say for an example, maybe if you have exponential functions mixed with trigonometric functions there, but a mixture of functions in a function. So to factorize, or maybe letting y equals to 0 to get x, it won't be easier to use the method that you know. So we'll be applying this formula. So there's something that I want to specify. So normally our xn, let's say xn, or xn, sometimes we can identify if, let's say, they say that if, let's say, you'll hear the word close to. So the value that will be given, they say, is close to, or maybe you hear that it is between. When you hear it is between, when they say it's close to, then that will be xn. But therefore, xn, if they say it's between, it means that if it's between x1 maybe plus x2, all divided by 2, you'll average between two values. That the root is between those values. So we'll be saying x1 divided by x2. But I wanted to draw these two information, these two notes here. But in other case, sometimes if you have let x equals to 0, you can even approximate using table method. So when you see that y, it's either is equals to 0, and then you see that the values where the root is between, maybe it might be -1 and -2. So you still apply this method from the table method. So I just want to take one example then in your book. It says it's 1. So if let's say we're given f of x equals to x cubed minus 3x plus 1, we need to determine the turning points of f of x. We need to determine the turning points of f of x. If we're looking into number 1 then. So we need to determine the values of f of x. The turning points of f of x. So we'll remember that. In fact, let me do a quick drawing of a graph. Quick drawing of a graph. I think the other time we used this means graphing. So to have a rough sketch of that function. So if let's say we have x, it's x cubed minus 3x plus 1. Yeah, so we wanted that rough sketch. So yeah, let's say we have that function. Let's say 2 value here. I don't know what is the value. So I just wanted the rough sketch so that when we do a simplification, for an example, let's say that is the rough sketch there. So we want to determine the turning points of this function. We want to determine the turning points of this function. So we know that at the turning point, we have a flat line or the rise over run there, give us m equals to 0. Give us the gradient there, it's equals to 0. The gradient there, it's equals to 0. So we know that tan at, tan theta, maybe if you say up, we still get 0 at 0. So, but I want to build something that we understand, or we know that the change in y or change in x, it gives us the equation of the gradient. And we know that at the turning point of any function, it can be a cubic function, a parabola. We mentioned the sine graph, the cosine graph. At the turning point, the gradient is 0. So this will help us if we have derivated the function. We know that, we can now determine the turning points or the critical values, which are x values at the turning point. So let us derivate the function. So we'll have f prime of x, which is equals to 3x x squared, right? Minus 3. So therefore, we know that, the derivative of a function gives us the equation of the slope. And therefore, we know that at the turning point, at TP, therefore, what is happening? M is equals to? It's equals to 0. So therefore, now that's why we let f prime of x equals to 0 minus 3. And therefore, we can now solve for s. So we can divide on both sides of the function by 3, or take 3 to the other side, divide, and put a square root of plus or minus. So 0 is equals to x squared minus 1. So if you factorize or take 1 to the other side, it's still the same. You can just factorize. This is difference of 2 squares. Factors of x squared is x and x. Minus 1 plus 1. Therefore, x value is equals to 1, or x is equals to minus 1 at the turning point. At the turning point. So when we like I said, we must calculate the values of the turning point, determine the turning points of f of x. So here we just calculated the critical values or the x ordinates. We need to calculate the y ordinates. So we know that into the original equation, we're going to substitute y. So it's either you can say f of 1 plus or minus 1. So we have 1 to the power of 3 minus 3 into 1 plus 1. So we have negative 1. And the other one, if let's say it's f of minus 1 plus 1. So it's negative. It's positive 3. So we have positive 3. So we know that turning point number 1. So x is 1, y is negative 1. And other turning point, if x is negative 1, y is 3. So these are the values of the turning point. Values of the turning point. So we are asked number 2 there, 1.2. We are asked to draw up a table of values of x and f of x where is ranging from x equals to minus 2 to x equals to 2. So we are going to draw down a table and say that if let's say x plus 2, 1 is y. So we must range the value from minus 2. So you can step by 1 unit or maybe by 0.5. So we can let's step by 1 unit. So negative 1, 0, 1, and 2. So we need to determine what is y or f, what is f of x. So we can use a calculator. There's too far. Or you can just substitute the values in one by one. Like if you say negative 2, but did you calculate everything? So if you use a table method, I think you'll say note and table number 3 using the calculator. What is it? This calculator. Casual. Table number 3. And then from there it will say f of x. Therefore, x will say shift, or it's alpha. Alpha is in red. So say alpha, you look for x there. Then you square, it's cube. Say minus 3 alpha, you look for x. Therefore, you say plus 1. And say equals 2. If it says g of x just put 0. If it says g of x, just say 0, then equals 2. It says start, say negative 2 equals 2. Then it says end at 2 equals 2. And then step 1 unit equals 2. So it gives us all the values. So at x equals to negative 2, what is y? Negative 1. Here is 3. Here is 1. Negative 1. Positive 3. So we have drawn up the table there. So I think the second question was asked to draw a neat graph of f of x between these values and show the turning points on it. So we're asked to do this. So the part that we have done in the beginning. So I wanted for a rough sketch here but you need to know how to draw these from the values that you have calculated. So put the turning points there in the graph, and we know that at minus 2, we said we have -1. The x is -2, we have -1, and then somewhere there. So let us inspect the second part. It says we need to a negative root of equation f of x equals to 0 is approximately negative 1.9. They state that if f of x equals to 0, then the negative root, it means that it is between here, for example, in this side. So that is the negative root. Remember, that's where f of x is 0. So we'll be looking into this party somewhere there. So it's on the negative side. So they say it's approximately. So we'll use this as our initial value. They say that the negative root is of the equation of f of x is approximately negative 1.9. So we need to use Newton's method once to find a better approximation of this root rounded off to 4 decimal places. So we have to use it once. The Newton's Raphson method, the Newton's Taylor method. And or into 3 decimal places. I was reading the second one. So into 3 decimal places. So we need to find a better approximation. So a better approximation, we want to find at least the value that is closer to the value that we are looking for, the root here, not the function. So normally if we were not given if it's approximately negative 1.9, we're supposed to inspect from our table here that what is if we can inspect where f of x is if approximately 0 is between 1 and 1. So by inspection, if I'm looking at -1, it's after 0. I'm looking at +3, it's after 0. The other one is before 0. So which means between the two values here, that's why we have f of x equals to 0. And another value again, somewhere here, this is positive, this is negative. It's either it might be between the two or between these two. In fact, this one we already covered here. It's this one, it's this one. So it's either it's between 1 and -1, or it's between -1 and 3. So we're supposed to approximate in that way. But if we're given the initial value, it's not waste time. Let us go and substitute that. Let's state that if that is, we can call this x1, can say x1, can say xn. It's the initial value. So, but let's look for x2. When we're looking for x2, we have to say that x1 minus f of x1 all divided by f prime of x1. Therefore, we can substitute now. The initial value is -1.9 minus. We need to substitute it to the original equation, the x1 value. Original equation is there. So where we substitute -1.9, all in all to the power of 3, minus 3 into -1.9 plus 1. Then we need to divide our better approximation there by the f prime of x. We did the derivative this here. So this is our f prime of x. So f prime of x is 3x squared -1.9 all squared minus 3. So they said we must use it one up in, and then leave it answer into 3 decimals. Okay, so what is the answer? -1.9 minus fraction -1.9 to the power of e minus 3 and bracket negative 1.9 plus 1, all divided by 3 into negative 1.9 all squared minus 3. Yeah, so what is the answer? Negative. So it's negative. So it's negative 1 point 3 decimals. 8, 8, or 889. Okay, I hope you're getting the same bill. So they are better approximated root. It is negative 1.889. So that is the root. I hope you got the same answer. I hope you got the same answer.